So hello everybody, we are starting right now and we are in direct connection with Cambridge with two scientists there and they will have to introduce themselves right now. I am Enrique Barra, I work for Global Excursion and we will talk now about nanotechnology and their work in this field. Right? Our first step today is a video that they will tell us about. Please, whenever you want, you can control the video, and if you pause it or if you start or you move, we will see everything.
Okay, perfect. So I'll quickly introduce the people. So I'm Mike Scherer, and this year is Tom Mitchell, and this year is Harry Benson. So yes, we are going to explain a bit about the SEM, and I think we'll just start with the video, and Harry is going to explain that. So here you just see the.
Okay, so this is a video now looking at a fly's eye under the SEM. What we've got here is the stage. So the stage with what are called stubs on, and the one underneath the you can see the fly is mounted on a stub on top of the stage, being raised now towards the end. We're looking now zoomed in at the surface. The fly is compact, so it's made up of very many lenses, and we're looking now at just a single lens. So so you can see down in the bottom left-hand corner, there's a scale bar showing that the features here are sort of 100 nanometers up to around 2 microns. This is at the most zoomed in, and if we just carry on playing the video, we're going to zoom slowly out. So it's a larger length scales, and you'll see this is the surface of a single lens now on that fly. So the video started again. Zooming out now from that lens, you should soon see that is one single lens, and now measure the width and height of it. Lens scale. Height here about microns. Width is similar. Clearly, it's the object. Yes, it's about 20 microns. The compound eye of fly is made up of very many of these lenses. Okay, sorry, I'll speak louder. The compound eye is made up of very many lenses, but the carry on zooming out, you'll see the array of here. They're all identical.
So, wait, we can't hear you very well. Can you raise your volume up again with the mouse over your video?
It's already at full. I'll just try and speak louder. But yeah. So this is now, you can see the whole compound eye on the fly. So
okay, I hear you better now. Perfect. Thank you.
Okay. Try and speak loud.
Okay, Enrique, I think now if you just swap back to the presentation, then we can show you.
Presentation, right?
Yes, please. You
can control now.
Okay, perfect. So here you can just see a photo of the SEM we are using, and on the right hand side you've got the PC and the monitors, so that's the control unit, and on the left hand side, so the top bit is where the electrons are accelerated, and the bottom bit is where you have your sample sitting in the chamber. So this is a vacuum system, and since the electrons are forming a beam, and they typically interact strongly with gases, so you really have to pump down the chamber in order to get a really good vacuum to be able to image different samples. So I'll go to the next slide. And this here is a illustration of the gun and the lenses of the SCM. And you could see that at the beginning of the video Henry showed you, you could see actually these lenses. And so the electron beam is focused into a really, really small spot using electromagnetic lenses and the electric field and magnetic field. And as you can see at the bottom, the beam hits the sample, and then electrons are reflected back or scattered back into this lens. So this is an in-lens detector where the electrons are detected, and then you generate an image from that. So I'm going to explain in more detail how this is happening. So there are a few different kinds of electron microscopes, and this one is a scanning electron microscope, and the other one would be a transmitting electron microscope. And coming back to the scanning electron microscope, here the electrons are focused in an extremely small point, and you scan the sample. By scanning it, you create the image. So, for example, you focus on a small spot that's roughly around 1 nanometer big in diameter, and then the electrons that interact with the material you try to image are scattered back into this into the detector you can see here, and then the electrons are in a crystal are transformed into light. So there's a crystal that where the electrons induce small or a few photons, and then the photons are counted using basically a solar cell. And depending how many electrons the detector detects, the pixel you see on the computer gets brighter. So the number of electrons detected per spot give feedback on the monitor. So if there are a lot of electrons scattered, the pixels on the monitor will appear brighter. So that's how you actually get the image in your scanning electron. And while scanning, you look at all the different spots, and then you calculate the whole image. So you scan along the sample in a raster fashion. So it's pretty similar like the old TVs we used to have. And here's a more like detailed description of what is happening. So you have your sample, you come in with the incident beam of electrons. So the thing is, maybe let's go one step back. Normally the resolution in an optical microscope is limited by the wavelength of the light. So because the wavelength of optical visible light is roughly between 400 and 800 nanometers, you actually can't image structures that are smaller than say 400 nanometers. And so electron microscopes are able to image structures that are around 1 nanometer to a few angstroms. And the reason for that being is that you can also describe an electron as a particle with a wavelength, and that's the Boyer wavelength. And depending on the electron, the wavelength gets smaller as you can see here, the interaction of the electron beam with the sample creates a lot of different things that are, for example, you have X-ray developing, then you have electrons that are backscattered, and you have secondary electrons. So these are electrons. Imagine the electron of the beam hits the sample, the atom here, then in the orbits, in the electron orbits, you can kick out one of these electrons that are associated with an atom in the sample, and these are the secondary electrons you then detect, for example, in the in-lens detector I showed you previously. And I also mentioned before that you can look at the electrons that are scattered, so in transmission, and that would then be a transmission electron microscope. So are there any questions so far, Enrique?
There was one question, but Sue answered it. It was about the kind of samples that you most commonly use with these kind of microscopes.
So,
but Sue said, answered it, but maybe you can complete it. And she said it was silicon devices. Yeah,
so you have to distinguish between the transmission electron and the scanning electron. So for the transmission, you normally only look at samples that are extremely thin, so just a couple of hundred of nanometers. Otherwise, the electron beam can't penetrate through the sample, and you're not able to see anything. So you have to use samples that are so thin that they are actually transparent to the electron. And that's totally different. The scanning electron microscope, the one we showed you the video a few minutes ago, you can actually look at all different kinds of samples. So typically, you want the sample to be conducting electrons, otherwise you build up a charge and then you distort the image. So what we typically do if we, for example, look at tissue or organic materials that don't or aren't conducting, we have to sputter these with an extremely thin layer of a noble metal like gold or platinum, and so they become conducting. But then actually we can look at anything we want, butterfly wings, nanostructures, different metal oxides, so there's actually no limitation. The only thing that sometimes is tricky is if you look at cells, because they have water inside, and as I mentioned before, the whole SEM chamber is under high vacuum, and then typically the cells just start to blow up, but there's a way around that. So you can keep the gas inside the chamber, so don't do the really good vacuum. You can also look at cells, or you can freeze the cells, for example. So, yep. Let's go to the next slide.
Yes, there is a small question also from the chat from Barbara. How expensive is such a microscope?
Sorry?
How expensive is such a microscope?
It really depends. There are high-resolution microscopes that cost up to a few million, but I think the one...
€1 million?
Yes. So, like high-resolution transmission electron microscopes, I mean, they fill up a whole room. So we've got one here in nanoscience, called the Titan, and they are really expensive. So, these are huge systems, and you also need people who operate them. So they also, the running costs are pretty high. And the SEM is roughly, I think, 250,000 pounds or euros. In the next slide, you can just see we use like nanostructures, and these are typical polymer films, and we use them to nanostructure metals. And I just skip this. So the structure you can see here, this is a SEM image of a polymer phase separated and form a structure called gyroid. And the scale bar you see here is 300 nanometers. So the structure is pretty small. Just for those who don't know what a nanometer is 10 to the power minus 9 meters, so extremely small. a billionth of a meter. So, and then when we use these porous polymer films as scaffolded templates for metals, that's how the metals look. So again, you see this wiggly structure, which is a three-dimensional structure, and the diameter of one of these structures is only 10 nanometers. So this is really extremely small, and so this is about 1 nanometer. These are extremely small samples. And Enrico, I think if you start one of the videos,
to the video, okay.
Zoom into one of these diode structures.
This one, right?
Perfect. I'll just start the movie.
Yes. Try to speak as loud as possible because sometimes your sound comes and goes. It's because of the microphone. I think you have a microphone integrated with the webcam. So
Yeah. Should I
sorry.
check out the webcam?
Sorry. Let me change.
I think the video doesn't work. What?
Yes. Let me 10 seconds.
Okay.
Because I deactivated the insertion. Sorry. I will try again. Now it should work. Now you can control it.
Okay. Should we just pluck out the... Okay, so now you see again we are zooming into the sample, and as we're getting, like you can see on the bottom left, the scale bar shows that we are zooming in, and right now we are just looking at 2 microns. It's getting smaller and smaller until we end up at roughly 200 nanometers, and these crystal-like shapes are made of this gel material. And you can see there's also a nanostructure here. And I'm going to zoom in even more in a second. And you really can see the nanostructure.
Yeah.
Okay?
So you have a win. Yes, Barbara asked, and that if you can repeat, what are we looking at here?
So this is diode, that's platinum, and the structure is called gyrite. So it's a 3-dimensional structure, and it should, I don't know, the movie stopped, but it should continue.
Yes, I stopped it. Sorry, because of the question.
So so this, it looks like a crystal, but it's actually not a crystal. So it's a polycrystalline material. It's just the way we grow these, and it starts to look like a crystal. But yeah, now the movie is it continuing?
Yes, it should continue. I will put it in the middle.
Okay.
Now,
and then
from here.
Zoom in further. So as I said, it's made out of platinum. We used one of the polymer templates I showed you before to replicate them with using electrochemical deposition. And as you can see here, again, the struts are extremely small, and we use these materials for different applications, such as solar cells, batteries, and catalysis, sensors. So because we have an extremely high surface area, and again, here you can see this material is highly porous, and the small struts are made out of platinum. And platinum is a highly highly catalytically active, and so we also use these materials for water splitting and so on. Okay.
So Barbara asked, is it some material that you create artificially then?
Yes. So I showed you before when I showed you how we make these, we are using blocker polymers. So these are polymers that have a hydrophilic part and a hydrophobic part. So the one part likes water and the other one doesn't. And just like water and oil, they don't want to mix. They demix and form 2 phases. These polymers have 2 chains. One chain is as I said, hydrophilic and the other one hydrophobic. So they don't want to mix, and they start to demix. And then, since they are linked together, the two polymer chains, they start to demix on a nanometer scale. And then we remove one of the two faces, one of the two polymers, and get these porous templates, and then we replicate them with the metal. And that's exactly what you see. So these are artificial structures.
Okay. And I have seen that you have a Windows program, right, to control the microscope. You have an interface, a Windows interface.
Yeah. Yes, that's a Microsoft interface, but the software comes with the microscope.
Okay. Great. So should we come back to the presentation?
Please.
Yes. I think it was slide 5, 6. You can control it.
Yes, the next one. So, and the next video we want to look at.
And before you start, there is another question in the chat from Samar El Kousa. What was the first thing identified with an EM? Do you know something about EM history?
So the first TM was made in 1930, and we have to check that. I can't. Let me come back to that question in a minute, okay?
Okay, perfect.
I'll follow that up.
We'll continue with the presentation, right?
So, and now the next thing we're going to look at is at a butterfly. And so on a butterfly, you have extremely small scales that create the color. But this color is kind of special because it's not due to pigments, but to the structure of the material. And so in the presentation, you see a morpho butterfly, which is like really shiny blue, and it's iridescent. And next to it are soap bubbles. And so normally, if you look at the soap water, it's transparent, right? So the material is actually transparent. But as soon as you form a really, really, really thin water soap film in the bubble, suddenly the water becomes colorful. So the water or soap bubbles, you see all the rainbow colors. And this is actually due to structural color. So the light interacts with the structure, with this extremely thin water film, and creates all these nice iridescent colors. And this is also what this morpho butterfly is doing. So there's a slide missing. Sorry. Yeah, I'm looking for this slide. Sorry. So as you can see here, there are two different mechanisms and color is generated. So the one mechanism is using pigment. So this is how normally everything is colored like this. So you have a pigment that absorbs different components of the white light. So the sun produces white light, and the different colors of the white light are absorbed by pigment. For example, when a pigment appears to be red, then either the yellow and the blue light are absorbed by the pigment, and the red light is reflected. That's how most of the colors are generated. For example, leaves of plants, they appear to be green because the chlorophyll absorbs mainly the blue and the red color. So, and the green color is reflected. So this is totally different. So on the right hand side, you see how structural colors are generated. For example, you have a multi-layer stack here, and depending on how the light interacts with the different, how the light interacts with these transparent structures, you can either reflect the red light and the blue light is transmitted. And this is, this is normal interference. And yes, so we are going to look how this morpho butterfly actually generates the structure. And before I come to that, let's have a look at a different butterfly. So this is a butterfly that actually uses a layered structure to generate the color. And you can see the butterfly has a small, like reddish blue spot at the bottom, which is generated by these multi-layers. And this is coming back to the in the middle, picture B, that's an image taken by an electron microscope. So now we are going to the next slide, back to the morpho butterfly. And I don't know whether you have seen this butterfly before or like a video. You can upload on YouTube. There's videos there. The amazing thing about the blue color is that it's really iridescent. So as soon as you start to move the butterfly, it's really extremely tiny blue, which is made by these structural colors. And so there's some SEM images shown of the scales that generate this color, and the material they are made of is transparent. So we have another video zooming into this butterfly structure. I think Enrique could start there.
So should I put the video now, right?
Please, please.
I think it's this one.
Yeah, that's the one. So here we can see this is the most zoomed out version. So typically if you touch a butterfly, you have like a powder on your fingers, right? So these are these extremely small scales that cover the butterfly wing and that are also responsible for the color. And each of these scales produces the color. And repeat that again, so the material, chitin, these scales are made of, is transparent. So we can really look through it. And just by nanostructuring this chitin, the butterfly is able to create these extremely nice blue iridescent colors. So now we are basically down to one of these scales. And when we zoom in further, you can really see that these scales are highly structured.
What is the zoom? The microns or nanometers?
As you can see on the bottom left, those scales are roughly around microns. Now we are zooming in further, and so the distance shown on the bottom left is roughly 1 micron now, but actually the structure is much the structure that is responsible for this blue color is even smaller. I don't know, the new again.
Yeah, sorry.
Purpose, so maybe if you...
This is the last part of the video, sorry.
Now we are zooming in even further, and these small layers you see, they are actually responsible for the blue color.
And this is responsible for the color, okay.
It's white.
There is another question. The iridescence of the wings are due to the multi-layer or the macro pattern?
No, the multi-layer. So actually, so the butterfly I showed you before, you only have multi-layers there. This butterfly is a bit more complicated. So you have actually, we call them Christmas trees. If you look at the cross-section of them, they are multi-layers, but they are not continuous, and they are held up by a stem in the middle of the things. I'll come back to that in a moment. So the thing is, if you only have multi-layers, you typically still have, depending on the viewing angle, you have different colors. And the butterfly, this morpho butterfly, has only one really blue color, and because the structure that generates the color is more complicated. So you use the angle dependence that you typically have with structural colors. So another thing where you often see structural colors is, first of all, in the rainbow, and then also if you have an oil spill on water. So if you have extremely thin film of actually black oil, you see all the different colors. And typically when you look at the oil spill from different angles, you see colors. So that's the thing. These structured colors are angle dependent.
Interesting.
Yeah. So in order for the light, in order to get structured color, as I mentioned before, the wavelength of light is roughly between 400 and 800 nanometer, the wavelength of visible light, and the structures have to be of the order of the same length in order to interact with the light. And as you can see, this structure here we can see here is responsible for creating the structural color.
Okay, thank you.
And there's no pigment. So if you would look at bulk material of chitin, it's transparent. So that's really the amazing thing. And so you can actually see these butterflies. People claim if you're flying over the Amazonas, in the green of the Amazonas, you can see these butterflies, the blue light of these butterflies. And another thing is pigments normally degrade over time. So, I mean, if you look at a t-shirt, especially if you leave it outside in the sun, the color starts to faint since the light breaks down the pigments. And these butterfly wing scales, they just, as long as the structure is intact, the color will be bright and shiny for hundreds of years.
Okay, thank you. Should I come back to the presentation now?
Please.
Okay. Let me slide 10. You can control it.
Here we are back to the morpho butterfly, and so when you look at the bottom right picture, this is the structure in a TEM, so in a transmission electron microscope. And the video I showed you just now was using a scanning electron microscope, and this is a cross-section through the structure. And here you can also see why we call the structure a Christmas tree structure. You have the multi-layers on the side and the stem in the middle. And so in order to get these images, you have to prepare extremely thin slices of one of these scales. So we have to use a microtome, so a really sharp knife, and create thin layers, and then we can look through the structure. So this is the transmission electron microscope image. And so this gives even more insight into the structure. And we are actually in the lab currently trying to replicate these structures. So at the top image, you see a transmission electron microscope. At the bottom image, those structures we recreated with metal oxide. These structures are slightly bigger, and the bottom image was taken using SEM microscope. And so there are quite a lot of different butterflies that generate colors in a different way. And here is a papilio butterfly. And the color, the green color you see, is also generated by structural, as a structural color. And so picture B shows just an optical microscope image of the different scales. And as you can see, you have different colors coming back from these scales. And then if you look at these scales under the SEM, which is shown in pictures C and E, you can see that there are small cavities. And as I mentioned, sorry?
Yes, I see that very well.
Okay, and so the SEM images only show you the topography of the structure. So you can nicely see these concavities, but you actually don't know what's happening inside the material. And here again, we use the transmission electron microscope. So we prepare thin slices of these scales and then put them into the transmission electron microscope and can look through them. And that's what you see in figure F, where you can see a slice or a cross-sectional view of these concavities. And as you can see, they are made out of multi-layer structure. So again, this transparent chitin and air. So, and the refractive index contrast of these two materials then leads to the interaction of light with these structures, which generate this beautiful green on the papilio butterfly.
Mm-hmm. So what are the scales of C and D? Pictures C and D on that slide?
C is also a SEM image of the same structure. So coming back to figure B, so the scale by here is 100 microns. So that's taken with the optical microscope. So you can zoom in a bit more with the optical microscope, but around like it's really hard. So this is already borderline what you can resolve with the optical microscope. You can do a bit better, but as I said before, the wavelength of light is of visible light is between 400 or 300 and 800 nanometers. So you can't really resolve spots that are smaller than 400 nanometers. And on the right hand, so figure C is a SEM image of these scales. But you could zoom in even more with the SEM. That's what you see in figure E. So you can see the concavities on the scales. But if you zoom in even further, you really nicely see these. And on figure D is even more zoomed in version using optical microscope. And here you can see how this green color actually is made. So in the middle of these concavities, you reflect yellow light while you reflect blue light at the border of the concavities. And together, the blue and the yellow light create this nice iridescent green appearance of the butterfly.
Okay, thank you.
And so there are even more animals that use structural color, such as birds and beetles. And actually, this beetle makes a really nice golden color and also blue and green colors. So that's a Japanese blue beetle. And again, if you move this beetle around in the sunlight, it's extremely shiny, and these colors are really amazing. And the way these beetles make these colors are again using transparent chitin multilayers with air. And in this case, actually the distance between the multilayers changes, and that's how these beetles even get really extremely nice and shiny colors, even whiter than the ones of the butterflies. And so there are also fish who use structural colors to create colors. Yeah, I think this is the end of the presentation. So Harry and I would answer more questions.
Okay, so should we finish here, or maybe we can try with the iPad right now? I don't know if Sue is still right there.
I think Sue took the iPad. We could try again. So are there any questions?
I'll try again, just in case. I don't know what could happen.
Are there any questions?
Are there any further questions? No? How many people are working in your lab?
No, that depends. There are different groups, but here in the Nanoscience Center, there are roughly, I would say, 50 people working here, but people come here from all over the University of Cambridge to use the facilities here. So actually the SEM is booked the whole day, so people can book slots from half an hour and up to 2 hours, and it's basically booked up all the time. And so we have an extremely big clean room here. So since the structures we are generating are extremely small, we have huge problems with dust, and so we have to filter the air, and we have a big clean room to prepare our samples here. And there are roughly 50 to 100 people using the facilities here.
So do you do any other dissemination activities like with a school or universities?
Yeah, we have physics at work here. So then school children come here every year and have a look at the physics department, and we also have an outreach program of nanoscience center here. So there used to be people going to schools and bringing some experiments and demonstrating them. So, for example, like these structured colors, we have a few experiments we do with school children. So we generate these like soap bubbles and then explain how these colors are, how they arise, and we can also fabricate thin layers of polymers that are also transparent, and then suddenly you get really nice colors. And there's the Cambridge University Science Week every year here in Cambridge, where there are also demonstrations in March. So and where there are demonstrations. But I think so if there are schools that are close to Cambridge, if you just write the researchers an email and ask them whether there are students or PhD students in the group who are willing to demonstrate a few of the things, I'm pretty sure most of the people would be really happy to demonstrate their research. And they're really sometimes interesting things. So, yeah.
There is a student question from Spain. How many EM are there in the world? Do you know a precise number?
I don't have a precise number, but there are quite a few companies selling electron microscopes. So you have, so in West Cambridge, just so that's the part where physics and parts of engineering are, and we have 10 electron microscopes here. So we have a couple of high resolution TM microscopes. We have a lot of SEMs, and actually there company, I think Hitachi, they are selling SEM, which is really just a box that you can carry around, and the resolution is actually pretty impressive, and that's a low vacuum system. So these systems aren't that expensive anymore. You probably can, I just have like a guess, probably around £50,000. So I saw one of those. So they're really just maybe 50 by 50 centimeters. So they're small. So you don't actually need that much in order to build a microscope.
Okay. Daniela Ambrosi from Italy, I suppose, asked, are there Italian students in your crew?
Yeah. So we have one in Sylvia. She is from Florence, and she's actually also working on structural colors. So I can send the link. So I can quickly get the link from our group. So we also have some information about our research online. And so Sylvia from Italy, she's actually working on structural colors. So you can find these structural colors also in plants. And some of the plants also generate their colors using structures on the nanometer length scale. And Sylvia is working on that. And then we have Stefano in our group. He works on nanostructures as well. So yeah, here in Cambridge, there are quite a lot of students from all over the world. So I think here Harry sitting next to me is one of the few persons who are actually from the UK. So I myself, I'm from Germany, and there are a lot of students from China, from Spain, from Italy, Korea.
Very multidisciplinary and multicultural, yeah.
So I just posted, or Tom posted the internet link from our group. So if you add a /Diner, So that's the side of the sector. So this is biological and soft systems, and when you go on people.
Okay. Yes, I co-browsed the URL that Sue added there in the chat, so I shared so everybody can see that.
Okay, and I went to our homepage, so you will find more information about structural colors there, and you can always drop me an email, and if you need more information.
Okay. From Taina Micheli, there is another question. What are the industrial application of your researches?
Well, basically, so we are working on a lot of different projects here. And for example, I'm working on batteries, on solar cells, and we are using the gyro structure I showed you earlier. We are using these materials for batteries, because here you really need extremely high surface area materials. So, I mean, applications are obvious. And then, so for example, the structural colors we try to make. First of all, you can, I mean, on banknotes, you already are using structural colors. These are these holograms you can see on banknotes in order to make these banknotes counterfeit protection, basically. And that's one application here. And you can also use these structural colors, for example, to make even whiter makeup, or there are also some also on to make colors on clothes. So this is actually coming. I know of some fabric that's actually iridescent as well. And then, of course, we are also trying to make different colors, for example, cars that are really tiny. And there are some videos online. So there's a video of iridescent car. So these structural colors are also really interesting.
Wait, I think I lost your audio. Now? Can you try again?
Okay. So,
okay, now, sorry. Yes, there is another question from Emilio Otero. Are usually complementary SAM and TEM images in research?
Yeah, sure. So we use both SEM and TM. As I mentioned before, SEM only gives you information about the topography, and TM actually gives you information within, like information about sample material. So when you go to TM images, you can also you really see. First of all, TM, the resolution is much higher, so you can resolve angstroms. So this is tens of nanometers, and you can really see individual atoms. And you can also see how these atoms are packed. So you, as soon as you look at the TM image, you can see whether the material is crystalline, amorphous, or polycrystalline. And you can also get diffraction information from that. So yes, these are highly complementary. So we use both SEM and TM for most of our samples. So also, for example, SEM, like the first slide I showed you, or the second slide in the presentation, when the electrons interact with your material, you also get X-ray that are backscattered. So when the electron beam hits the material, you start, so the electrons interact with material, and you start to so in an atom you have the different electron orbitals, and the electrons in here, if they are hit by one of the electrons in the beam, you typically remove that electron, and when that electron is replaced, you start emitting X-rays. And these X-rays are specific for different materials. So the energy of the X-rays can be detected with a different detector in the XM, and from that you can tell what kind of material you're actually imaging. So yeah, the coming back to the question, SEM and TEM are highly complementary.
Okay, and there is one last question I think I lost from Evita. What is your day-to-day job like in the lab? You know, do you
Well,
work all the time with your microscopes, or do you know other kind of researches?
So, first of all, in our group, we actually prepare all these nanostructures we are looking at. First, it takes quite a lot of time to make these structures, and then in order to characterize them, we take them to the SEM to have a look what we actually got. And this is really crucial because there's no other way really to detect what kind of structure we have in our samples. So we prepare samples, take them to the SEM, look at the samples, see what kind of structure we have, and then make more experiments on these kind of structures. And yeah, I really like my work here. It's really interesting. We are basically free to do whatever we want. So we have different projects. We work on batteries, solar cells, these structural colors, and yeah, I think it's highly interesting.
Thank you. So I think there is no more questions. So maybe it's almost 3 o'clock. So maybe we should finish here. Thank you very much.
Thank you a lot.
Was everything very clear? That's a pity that we could not join with the iPad so we can see the electronic microscope in real time, but thank you very much for all your presentation. It was all very clear. Thank you.
If you're interested, you could make a short video and put that online as well.
Okay.
We could, because we also have a nice TEM here, like huge machine, and yeah, we could definitely make a small video and put that online in a few hours.
Thank you. Thank you also to all the teachers and schools participating. So that will be all.
Yeah, we'll do that.
Thank you. Bye.
Okay,
Bye.
thank you. Bye.
Thank you.